So was your triangle, was your figure actually a right triangle? Of course, you could repeat that investigation with another set of Pythagorean triples, but the Egyptian rope stretchers were not wrong. The converse of the Pythagorean theorem is in fact true, that if we have our side lengths where we take the longest one and we square it, and then we compare it to the squares of the other two sides, and if it's equal, we do in fact make ourselves a right triangle. Okay, so here for your notes is the converse of the Pythagorean theorem. Let's write something down. If the square of the length of the longest side of a triangle is equal to the sum of the squares of the lengths of the other two sides, then it is a right triangle. In other words, if c squared is equal to a squared plus b squared, and you can see that c here is our longest side, it's across from our biggest angle, c squared is equal to a squared plus b squared, then our triangle ABC is in fact a right triangle. Okay, so let's take a look at a few examples. Here's a multiple choice kind of standardized test example. Which of the following is a right triangle? And I have triangles that if I were to take a protractor or the corner of a piece of paper, I would notice that each one of these things is definitely drawn to be exactly a right triangle. So I can't use a visual inspection. I actually have to do the math on it. I have to check to see if the biggest side, c squared, is equal to a squared plus b squared. All right, let's scroll down here. There we go. And let's just check it out. We want to see, obviously the 27 is the biggest. Is 27 squared, is it equal to, boop, 15 squared plus 20 squared? Let's break out our calculator. Let's make a new one, a calculator. So we had, what was it? Was it like 27 squared? I think it was 27, yeah. So 27, we're going to square that thing. And we're going to see, that's 729. All right, fine. See if that's equal to 15 squared plus 20 squared. It's sure not. Nope, it is not. Let's go back here. Oh, it's not. So this one definitely not a right triangle here. Okay, then here obviously the 20 is the biggest one. So we're going to see, is 20 squared equal to 12 squared plus 15 squared? What do you think? 20 squared. Is it equal to 12 squared plus 15 squared? Nope, it is not. Oh, you were close. 369 and 400, you were close. It's not a right triangle. All right. I got a pretty good feeling about this next one here. Is 30 squared equal to 18 squared plus 25 squared? I don't know. 30 squared, 900 of course. What were our other two numbers? 18 squared plus 25 squared. Ooh, no, actually it's smaller this time. Not a right triangle. Wonder what kind of triangle it is. It's not a right triangle. Okay, anyway. Well, by process of elimination, it must be this one, right? So apparently 65 squared should be equal to 25 squared plus 60 squared. Let's just check it out. Check it out. Let's verify that actually works. 65. Let's square it. Is that equal to a 25 squared plus a 60 squared? It definitely is. We got 4,225, definitely equal to 4,285. All right. Now, there's another way to have tackled this one, and that's using Pythagorean triples, because if these things are whole numbers, they have to be Pythagorean triples. So let's look at our answer J here. 25 is 5 times 5. All of these have a common factor of 5 in it, right? So let's see, 60 is 5 times 12, and then we got 65 as being 5 times 13. Oh, look at this. Look, we have a 5, 12, 13 right triangle, and it's been scaled up by 5. So back in the other lesson, we just basically automatically assumed the converse of the Pythagorean theorem was actually true whenever we were using our Pythagorean triples. Okay. Hey, actually, let's go back here this way. It looks better. So on example 3, we've got this carpenter here. That's my grandpa. Not really. Anyway, the first steel squares were manufactured by the Eagle Steel Company back in the 1820s. You probably have one of these in your garage hanging on a nail or something. It's this L-shaped metal ruler right here that carpenters use to check to see if they have right angles or to actually make right angles, right? Okay. And there's like rulers on each side. Here's another one. You can see that sometimes you use it to make sure that your haircut is nice and flat and straight and at right angles. Prior to the invention of this tool, though, carpenters used just a good old-fashioned tape measure and the converse of the Pythagorean theorem. How do you think they did this? Well, they did it exactly like the Egyptians. Here, let me draw you a little picture here. Womp, womp, womp. Let's say that a carpenter is building a building, and let's say that this thing right here, this is a wall. You can see that it's a wall, right? I'm actually going to label it so it's official. And then let's say that I build another wall that I want to check to see is a right angle to that one. And all I have is a tape measure. So I take my tape measure, and on one wall, I measure from, say, this wall out, I measure, and I see 4 feet. I put a dot on here at 4 feet. Right? I'm going to put a dot there. I'm going to mark it with my pencil, maybe a point A or something. Okay. Along the other wall, I'm going to measure out, this time, 3 feet. Right? And I'll put a little dot here. I'll call that one B. And then with my tape measure, I am going to, maybe in green here, I'm going to measure the distance between the two dots that I just put on there. And if it is exactly 5 feet, I know, bam, that my two walls make right angles to each other. If it was more than 5 feet or less than 5 feet, somebody loses their job. So if I go back to the picture that opened this particular lesson, that's exactly what these guys are doing here, is that they're measuring out along one piece, one of the Pythagorean triples. Hey, where's my laser pointer? One of the Pythagorean triples here. Another one, we're not seeing this other dude over here on this other side, but you can see along the length of the hypotenuse, they're checking to make sure that those things make perfect right angles. Right? The Egyptians, very, very smart. And really what it comes down to is like that formed, like we call it the Pythagorean Theorem, named after Pythagoras, but not because he discovered it, but of course he was just the first to logically prove it with other mathematics, which, you know, you guys got to do in the previous lesson. All right, so let's take a look at another example. The last one, I think, in this objective here. Tell whether a triangle with a given side length is a right triangle. All right. So we've got on number 1, 5, 6, 7, 5, 6, square root of 61, and 5, 6, 8. Let's take a look at each one of these numbers. All right, so the first one here, I always want to start with the largest one. So on number 1, 7 squared, I want to check to see, is 7 squared equal to 5 squared plus 6 squared? Well, 7 squared is 49. And that's a 25 and a 36. Add those together, that would be 50, 61. All right, so 49 and 61. Well, 49's not equal to it. Let's get rid of this box. This is definitely not equal, so this one is not right. It's just not right. That gets an exclamation point. Let's change colors and change problems. So let's look at number 2. So which one of these numbers is the biggest one? We got 5, we got 6, we got the square root of 61. Well, the square root of 61, between what two perfect squares would that be? Let's see, it's really close to 64, which is 8 squared, and it's bigger than 49, which is 7 squared. So this is someplace between 7 and 8, right? Closer to 8 than it is to 7. So it's definitely the biggest side. I'm going to put that one down first. Square root of 61, we're going to square that thing and compare it to 5 squared plus 6 squared. Well, The square and the square root, they cancel each other out, and I just get 61. We've already added up 5 squared plus 6 squared. We know that that's equal to 61. Check. We have ourselves a right triangle. It also gets an exclamation point. Okay. All right then. And then the last one, how about, I don't know, how about this nice color? Let's try it with this one. Obviously, the 8 here is the biggest number. So we'd have 8 squared. Compare that thing to 5 squared plus 6 squared. 64, we know, is not equal to 61. All right. So, yeah, this one's not right either. We only had one right triangle. Not right. Well, if it's not a right triangle, what other possibilities exist? Well, right triangle refers to angle measurements. So if it's not right, it could either be an obtuse triangle or it could be an acute triangle. So let's look at each one of these examples. Notice that on the first one, we'd had 49 is definitely not equal to 61. It's actually, it's less than, right? And then if I come over here to number 3, 64, definitely not equal to 61, but it's actually more than. So I wonder what kind of triangles they are. Well, tune into the second objective where we answer that exact question.